Alright, in this video we're going to look at capacitive reactance and see what it does. And as I hinted in the video on inductive reactance, it has an inverse relationship. Let's see if we can puzzle some of that out. First of all, let's get a diagram up here. Always like pictures. So we have our alternating current source, and this time we have a capacitor in there. And of course this is also our frequency. And as I had up there, we're talking about an alternating current. And we know the distance of one cycle, plotted out here, is 2 pi radians. And our frequency is how many of these cycles occur per time period. Now, we know that direct current cannot flow through a capacitor. It just appears as an open. Okay, but as we start alternating the current, and remember, reactance is the opposition to the change in the current flow. So we're talking about the change. Remember, in inductive, it took a while for that inductive field, that magnetic field, to build up around the coil and for it to collapse. Okay, well, in this particular case, we're talking about charging up the plates of a capacitor. At low frequency, this time that it takes to charge up is longer than if we increase the frequency, where this is bouncing back and forth. It's bouncing back and forth to the point where this appears to be a short. So as frequency increases, capacitive reactance decreases. That's an inverse relationship. So X sub C, then, it's inverse. Inverse means mathematically that we have a fraction, and oftentimes 1 is on top. And whatever is going on here is on the bottom. Well, it's not too dissimilar from our inductor. We still want to know 2 pi F. Okay. How many complete cycles, that's 2 pi radians, how many cycles? We get that by multiplying it times the frequency, because that tells us how many times those cycles are occurring. And that's going to be multiplied by the capacitance. So our formulas then are really pretty similar. The difference being primarily that we have an L for inductors, C for capacitors, and since the relationship between the frequency and the reactance is inverse, we get this 1 over effect. Okay, so now that we know what the formula is, and we have some sort of an idea of why this is occurring, let's do a calculation. Let's keep the same frequency as we did for the inductor, 2.65 megahertz. And our capacitor, not X, we're going to be calculating X. Our capacitor then is 10 millifarads. I don't think they use the D much, but I just wanted to denote that. So again, all we really need to do is plug that into our calculator. And there's always more than one way to calculate things, But I like just kind of entering it in the way it is. And I'll show you how I do that. Clear us out here. We know that this is an inverse relationship. I could go through this calculation and do the -1 thing, but let's just put it in like it is. Let's put it in by 1 divided by. Now, since I have multiple players here in the denominator, I like to put the whole denominator in parentheses. Otherwise, the calculator may not interpret what I want correctly. So I'll open a parent, and let's do our 2 times pi times our frequency, 2.65 times 10 to the 6th power times, now milli is -3, so that is 10 times 10 to the -3, and close my parenthesis and press enter. And this gives me a value then of, let's just round it to 6.0 times 10 to the -6 power. That's not a lot of resistance. This is taking the number 6, and where its decimal point is here, let's move it here. 1, 2, 3, 4, 5. Let's see. 1, 3, 4, 5. Did I get that right? 1, 2, 4, 5, 6. I got one too many zeros there. That happens in the best of families. Okay. That's ohms of reactance. So pretty much at up in the megahertz, this thing, while it offers some, it's not much. The higher the frequency goes, the more, the less the reactance is. It drops to where it just pretty much looks like a short. Okay. So we see then that basically it's the opposite of an inductor, where the reactance is directly proportional to the increase or decrease in frequency. Here, as the frequency goes down, the reactance goes up, or as the frequency goes up, the reactance comes down. All right, so you need to know this formula for reactance, and you need to know this formula for inductance. And then we're also going to do, I want to do a video on resonant frequency, because resonance happens when these two reactance values are equal to one another. Okay. More about that when we get to that video. See you then.